Jesteśmy technicznie.
I've got a master's in England, University of Central Asia. I have a PhD from University
So good afternoon, everyone. Today we are happy to host Fraser Gillan here. Fraser is a postdoc at the NCBJ, so National Center for Nuclear Research, working with a group of Professor Łukasz Wyszykowski. And Fraser is an expert in comets and also in asteroids and some interstellar objects, as we can see from the title of his talk. Was doing his studies and PhD in the UK, let's go in general. So, and you moved to Warsaw like half a year ago. So it was summer, over the summer. So the floor is yours.
All right, cheers, thanks. Yeah, so hi everyone. So my name is Fraser Gillan. I'm a postdoc at NCBJ working with Łukasz. And I'll talk today about my research. So I was looking at comets and asteroids, and then towards the end of the talk, I'll get into a little bit of interstellar objects as well. So just to begin, I thought I'd give a bit of an overview on the small bodies in our solar system. So there's two main types of small bodies. You have comets and you have asteroids. And you can think of asteroids as being composed primarily of rock, whereas you can think of comets as having this rock, but they also have ice and they have dust as well. So that's the main difference between the two, is this ice and this dust on comets. So comets come in many shapes and sizes. So typically they're a few kilometers across, up to tens of kilometers for some of the larger ones. And they have this irregular shaped nucleus. So the nucleus is that actual physical part at the heart of every comet. So on the right-hand side here, you can see this is comet 67P Churyumov-Gerasimenko. This was the target of the European Space Agency Rosetta mission that in 2014 actually sent a spacecraft to rendezvous and eventually land on 67P. But you can see this is clearly an irregular shaped nucleus here. And then I guess the main thing to ask is, why are we actually interested in comets? Why should we study them? Well, comets have basically remained unchanged since the formation of the solar system. So they can act as these sort of time capsules and give us insights as to what the conditions were like during the formation of the solar system. And it allows us to put constraints on planetary formation models of our own solar system, but also of other systems as well. So the comets in our solar system have two main origins. You have the Oort cloud, which is this sphere that surrounds all the planets. And this is about 10,000 to 100,000 astronomical units from the sun. So this is this cloud here, and comets can come in from any direction. This is the origin of the long period comets, the comets that are typically coming in for the first time and have an orbital period of tens of thousands to sometimes hundreds of thousands of years. You then have the second reservoir, which is this sort of donut-shaped ring just beyond the orbit of Neptune called the Kuiper Belt. And this is the region where all your short period comets come from. So you have different subclasses of short period comets. You have Halley-type comets, which have an orbit period of less than 200 years. And you also have Jupiter family comets here that have an orbital period of less than 20 years. So it's quite hard to see here, but you can see the Jupiter family comets here go out to about Jupiter. Halley-type go towards the outer solar system, and your long period comets will disappear for thousands of years. So just an animation here to show what this looks like. If you imagine a comet in the outer solar system here, out in the Oort cloud, this comet will be perturbed inwards due to either galactic heat or and not inner solar system. And then comes this long comet, and you can see the Kuiper inner solar much closer in is this donut-shaped ring just beyond the orbit of Neptune. So how do we actually name comets? How do they get their names? Well, back in 2022, there was this bright comet in the sky, as we have a couple every year. They make the news. But this is a good example to use. So the first part of the comet, the lettering, this denotes the type of orbit that the comet has. So if we have P slash, this is a periodic comet. This is a comet that's been seen on more than one epoch, on more than one time around the sun. We then have C slash. This is your long period comets. These are comets that are coming into the solar system for the first time. And these have these tens to hundreds of thousands of years orbital period. Then have D. These are comets that can get too close to the sun and they'll completely vaporize, or comets that will fragment and break up and they become lost. We then have X, which are very rare, but these are historic comets. So back when record keeping wasn't so good, and you maybe see comets written in like the history books, or even back when there's comet observations written on bones back in the ancient Chinese times. These are no longer known, the orbits of these, but these get this X designation. And then the most recent designation is actually I. So I'll talk about it a bit towards the end of the talk, but we had in 2017 the discovery of the first interstellar object, and that gets that I designation. So the next part is pretty self-explanatory. It's the year of discovery. For the next part, we take each month of the year and we split it into two. So the first half of January gets A, second half gets B, first half of February gets C, second half gets D, and so on. So for this A3 here, this means this was the third comet discovered in the first half of March 2022. And then finally, I think the coolest bit about this is if you discover the comet, you get it named after you. So in this case, it was discovered by the Zwicky Transit Facility, so it gets the ZTF designation at the end there. And just another couple of examples here. We have 67P, which was the 67th periodic comet discovered, named after Churyumov and Gerasimenko. And then recently we have the third ever interstellar object discovered by the Atlas survey there. So I'm going to focus today quite a lot on comet dust. So I thought it'd be useful to go over how we get dust from the nucleus of the comet into the atmosphere. So these comets are on these very elliptical orbits. They're non-circular orbits, which means they go through significant phases of extreme cooling and extreme heating as they get close to the sun. You have the frozen gas and ices on the nucleus itself, and that gas is embedded, that ice is embedded with dust grains. And as that heats up and gets close to the sun, that ice begins to sublimate. And as that sublimation occurs, that actually pulls the dust grains out with it. It causes a drag force on the dust grains and pulls the dust grains out into the cometary atmosphere. So on the right-hand side here, we have probably the most famous comet ever. So this is Halley's comet, or Comet Halley. This is the nucleus in the center here, as seen by Giotto in the 80s. This is actually called 1P Halley. So as you know now, this is the first periodic comet. But you can see clearly on the sunlit side of this comet, there's significant sublimation compared to the dark side of the comet, where it's not zero, but it's significantly less. And that's just because of that extreme temperature difference on the two sides. And again, this is from nearby from the Rosetta spacecraft. This is the cometary environment of 67P, and you can see our surface here in the back. So I thought it was just a significant amount of dust, and that's actually So just to summarize here, at the heart of every comet, we have the cometary nucleus. That's the physical part of the comet. We then have the local atmosphere around the comet, which we call the cometary coma, as you can see here. And then the most striking visual aspect of a comet are these cometary tails, which we see, make headlines, and we see them all over all the images that we look at. And comets actually have two tails. So they have the dust tail, and as you get the dust that sublimates into the atmosphere, it's the pressure of the sunlight itself. The solar radiation pressure is the only thing that acts upon these dust particles. And depending on the size of the dust particle, they'll accelerate by different amounts. But eventually you just get this dust tail that sort of lazily curves out behind the comet, and eventually it'll map out the orbit of the comet itself. We then have what we call the gas tail, or the ion tail, or the plasma tail. And this always points directly and straight away from the sun. So what we have is we have the gas molecules in the coma. We then have the solar UV light that interacts with these gas molecules and causes ionization. And then these charged particles, now that are ionized, get carried away with the solar wind directly opposite the solar direction. And it's quite hard to see here, but we do have the dust tail, and you can't really see it in the image, but there's a straight gas tail going up and down this way here. So all of the research I'll talk about for the first half of this talk today is using data from the Asteroid Terrestrial-impact Last Alert System, or ATLAS. So this is comprised of 4 0.5-meter telescope units, 2 of which are in Hawaii, 1 is in South Africa, and 1 is in Chile. And there's actually a 5th unit now on Teddy, but that's a totally different design, different filters, and different setup. So we're just going to focus on the first 4 ATLAS units here. So ATLAS has a very wide 7.4-degree field of view on the sky, which is roughly equivalent to about 15 times the diameter of the full moon. And this goes down to a magnitude limit of about 19.5 if you have dark skies and good seeing, etc. So it's a really high cadence survey as well. It scans about 80% of the night sky every single night, using these 2 non-standard broadband filters, which are cyan and orange. And that has a wavelength coverage of about 420 nanometers up to 820 nanometers. And then finally, ATLAS has been in near continuous operation since 2016. So there's a wealth of photometry dating back almost a full decade now in the ATLAS images. And this is one of the ATLAS telescopes from inside the dome on Haleakala in Hawaii. So I've talked a lot about comets and a little bit about ATLAS. So I thought it'd be nice to tie them both together and say, why do we actually use ATLAS to study active comets? Well, the reason is because they had this high coverage, because they're looking at these comets every single night, we can look at how they evolve throughout their orbits. So this is an example. This is an example comet here that we looked at. This is 327P in the center. These are ATLAS difference images. Comet Gillian increases, the comet brighter, the coma increases, and you can actually see a tail forming to the right here. And then as we move away, that activity ceases, and it gets a lot fainter towards the center. And this is over a span of about 150 days in the ATLAS images. So we looked at all Jupiter family comets that reached their perihelion, their closest point to the sun, from 2020 to 2023 over a 4-year period. So this gave us 116 Jupiter family comets. And in the end, it was over 34,000 ATLAS images that we used. So this shows all the comets that we looked at on the y-axis, and we've plotted it against the heliocentric distance, the distance from the sun, over which they're visible to ATLAS. So for example, if we take 4P Phi at the top, that pink represents the pre-perihelion visibility range. The star marks perihelion, that closest point, and then the black represents that post-perihelion visibility range. And then you might notice as well that the numbered comets from 4P down to 434P, these are all visible typically for a lot longer than the comets at the bottom that only have a provisional designation. That's just because these comets were brighter, therefore they were discovered earlier, so they're numbered, and the bottom ones are not. And again, this is just a bit of a graphical representation of what was shown there. This is the coverage that we're really getting, is when the comets are active on the way into perihelion, that closest point, and then on the way out again. And when the comet's out here, it's just the bare nucleus we're looking at, and it's really too faint to see in any of the ATLAS images. So we're just focusing on the active part of the orbit for all of these comets. So how do we actually measure the dust production rate in these comets? So we use this parameter called AF rho. So AF rho is a product of 3 factors, A, F, and rho, where A is your albedo of your dust grains. That's how reflective your dust grains are. So we assume a 4% albedo. We then have F, which is your filling factor. So if you center your comet within an aperture on the sky, you say how much of that aperture is actually filled with the dust grains. And then rho is the size of that aperture you use. So for example, on the right-hand side here, I've sort of crudely drawn, if you imagine, this is the aperture here, and this is the cometary nucleus in the center, and these are the dust particles around it. You can see that the filling factor on this top comet is less than on the bottom comet, i.e. the dust production rate and AF rho is less. And then finally, I'm not really the biggest fan of putting equations in slides, because I think sometimes they can be a little bit boring to look at. However, I think this one is important because it shows how robust a measurement AF rho can be. To obtain a measurement of AF rho, all we need is the flux from the comet in our measurements. Everything else can be obtained independently. This is the distance from the comet to the sun, distance from the comet to the Earth, and the solar flux at 1 AU. And these can all be obtained independently of your measurements. So to get an estimate of the dust production rate, all you need to know is your flux from the comet, again, making this a very robust measurement. So for each of these 116 JFCs, we made the exact same measurements. On our top plot here, we have a standard light curve of apparent magnitude versus time in MJD, where the orange and cyan points refer to the O band and C band in Atlas. And you can see as the comet gets close to perihelion, that sublimation increases, the magnitude also increases, and as we move away, that decreases as we would expect. We then convert our magnitude measurements to AF rho, that proxy for dust production. And again, we can see as that sublimation increases, the dust production increases, and then again, as we move away, that begins to decrease. Dust in comets typically are reflecting a lot of red light, so that'll be more sensitive to the orange band. So what we've done with our cyan band measurements is we've calculated an equivalent O band measurement. So these measurements should align completely if there is only dust in the coma. However, you can see that there's still an excess of flux in the cyan bands, in the cyan band measurements. So we can actually attribute this to gas emission as well in the coma. So the final thing we've looked at here is you may sort of almost naively expect at perihelion, at the closest point to the sun, this is when your energy from the sun will be a maximum. This is when your temperature will be a maximum. So you may think this is where the sublimation rate and dust production will also be a maximum. So what we've measured next is, where is this maximum dust production rate actually relative to your closest point? And you can see there's a little bit of a lag for this particular comet. So doing this for the whole population, this is the closest point to the sun for each of these individual comets. And then we've plotted where did you actually reach that maximum dust production rate relative to your closest point. And there's a few things immediately apparent. Number one is that the activity in general spans over 2 orders of magnitude, showing that there's some comets up here that are super active and they're getting rid of a lot of material on this passage. Whereas there's some comets down at the bottom here that are only very lightly sublimating and getting rid of very minimal amount of material. We have this group on the left-hand side here, and they're reaching their maximum dust production rate slightly before perihelion. And the reason for this, we actually attribute to what we call seasonal effects. So if you imagine the cometary nucleus on the way into the sun, there'll be one hemisphere that's completely lit by the sun and one that's not. So if that one that's lit by the sun on the way in has a lot of ice and a lot of material available for sublimation, that may reach a maximum actually slightly before. And then if you imagine on the way out, it has a different hemisphere eliminated, but maybe that doesn't have so much ice on it. Even though the temperature is greater, the sublimation rate is not going to increase anymore. We then have this next group here, which is actually the majority of our comets are reaching their maximum dust production rate slightly after perihelion. And there's a few reasons for this. So number one, again, it may be seasonal effects. Number two, we considered what we call thermal inertia. So that's the ability for an object to retain heat. So we were thinking, is it actually just taking a lot longer for the cometary nucleus to heat up? And then is that causing this lag here? But when we look in the literature, a lot of comets are not retaining heat. They're getting their temperature increase from the sun and they're almost radiating it away immediately. So that's not the cause here. What we think is it's actually just down to the observing geometry itself. So if you imagine looking at an aperture on the sky and a comet in the center, the fastest way the dust can leave that aperture would be radially outwards. However, if you have a comet in the center of your aperture and the dust and you're looking down the line of sight of the comet, that dust can remain in the aperture for a lot longer than it would if it was to just move radially outward. And then finally, we have 2 comets over here on the right-hand side that are reaching their maximum dust production rate almost a year after perihelion. But color-coded with eccentricity, you can actually see the orbits of these comets are a lot more circular than the rest of these comets. These are going through this extreme heat and extreme cooling, whereas these are going down very circular in comparison, and that heat is a lot more gradual. So the time of perihelion for these two comets isn't so much of an important factor. So this is a very similar plot here. And what we've done now is we've then said, instead of looking at days relative to perihelion, where do you reach your maximum? We've said if we consider each orbit individually, and we take your entire orbital period, what fraction of your orbital period are you reaching that maximum relative to perihelion? And what we find is that all comets reach their maximum dust production rate within 10% of perihelion distance. So I've shown you before, we have the magnitude and time plot. We have our dust production time plot, but then we've also measured the rate of change of dust production, the rate of change of activity as a function of heliocentric distance. So this is a log plot here. This is your dust production, and this is your distance from the sun. So this black line is the comet coming in. This is the closest point to the sun, and then this is the comet going out here. And what you can see is that rate of change of activity on the way into the sun is steeper than on the way out. So what this means is the dust is remaining in the aperture for longer post-perihelion. A couple of reasons for this. So number one, when you get close to perihelion, there's just more overall sublimation. But also, when you get close to perihelion and that energy is larger from the sun, you can sublimate larger and larger dust particles. And the larger the dust particle that's in the atmosphere, the longer it takes them to actually accelerate and leave the aperture. So this was an example comet here, but we actually find that this holds true across the entire population of JFCs. And we got statistically significant results to support this as well. But you can also see that there is a large standard deviation on both the measurements, showing that there is a wide range of these activity indices within the population. So why is this research important? Well, there's been previous studies that have looked at large surveys of comets where they'll look at long period comets, short period comets, and comets from loads of different dynamical classes. However, you can't make inferences on a single population by doing this. And also, there's been a lot of studies that have made these really high cadence observations of individual comets, looking at an outburst, for example, or a close perihelion passage. But again, you can't make inferences on the entire population. So what we've done here is we've used a single survey to make these high cadence observations of a single dynamical population, so that all the results are very intercomparable. So almost as a byproduct of looking at 34,000 images and 116 JFCs, we can look at some other little cool features here. So we measure outbursts in JFC versus material. An example may be, for example, on the nucleus, and it'll just eject masses of material very quickly. So this is pre to post outburst. I'm just flashing back and forward, and you can clearly see the significant amount of material that's been released here post outburst. And graphically, this is represented by this decrease that was going down and this sudden jump before that exponential decay here. Overall in our sample, the outbursts ranged from an increase in 0.2 magnitudes up to almost 3 magnitudes, all when they were very close to the sun. And these were also evenly distributed pre to post perihelion. So there were several of our comets. The comets I've showed you up until this point, I've shown an increase in magnitude and a decrease as they move away. Some of our comets, we had clear detections in the images, but no change in dust production at all. So this is consistent with a direct detection of the cometary nucleus itself. And because we know the size of the aperture we're looking within the whole time, we can then determine the actual size or the upper limit to the size of the nucleus itself. So we measured this for a few of our comets, and this ranged from about 1.5 kilometers in radius up to about 4 kilometers in radius, which is consistent with what we expect for JFCs, and was also consistent with literature values for the same comets. So these are some of the things on the side that we didn't go in to look for, but you can get for large survey data. So just to summarize this JFC section of the work, we measured dust production rates for 116 JFCs over this 4-year period, and to date, this is the largest study of JFC activity. Comets show this preference to reach their maximum dust production after perihelion, but we also show that it was important to consider each orbit individually. And then finally, the AFRO activity index, that rate of change of activity, is steeper at pre-perihelion than it is post-perihelion, implying that the dust remains in the aperture longer after perihelion. And then if you are interested or want to read more on anything, these are 2 papers that we have on everything I've just covered just now. So that's the end of the first study. I'll move on to the next section here. So all the JFCs that I've looked at up until now, all the comets we've looked at till now, are known to be sublimating. They're known comets, and they all start out here in the Kuiper belt. So occasionally you'll have perturbations from Neptune, and what will happen is these non-active nuclei, at the time essentially they're asteroids with ice on them, they'll begin to migrate inwards. So as they move from the Kuiper belt inwards, and they're in the region of the giant planets, they're then known as centaurs. And at this point, this is where the temperature can increase enough to actually begin sublimation. So at this point here, this is where you start that change from asteroid into comet. Before, what we've been looking at before is where they're fully fledged JFCs. So the next little bit of talk I'm going to talk about is this little transition region here from we're not active, never seen activity before, to now you're active. We're going to change the class from asteroid to comet. So the way we currently determine or detect new comets is just by the visual inspection of the dust coma itself. We look at the images and essentially say, is this fuzzy? We can also do PSF analysis as well to definitively determine this. We discover about 15 new JFCs each year. But we also are aware that there's a lot of asteroids that are on these JFC type orbits, and they've never shown activity. But because we're only using survey imaging, these surveys are limited by 30-second exposure times. They're only going to go down to 19th, 20th, 21st magnitude. So the idea here is we're going to look at asteroids on these comet-like orbits with deep dedicated imaging to see if we look deep enough, are they actually active? So back in 2022, we went to the Isaac Newton telescope on La Palma. So this is a, I guess, medium-sized now telescope. So this is a 2.5-meter telescope. We went on a 3-night observing run in November. And again, the idea here was to dedicate almost half an hour exposure to a single target to say that if we really hammer observations of these asteroids, they're actually active if we don't use survey imaging. So the way we determine activity, you take your asteroid in the center here, and you measure the distribution of flux as a function of radius. So you sum up the flux in the center pixel, you then take the next set of pixels, sum up the flux, and so on and so forth as you move out. And the idea here is you look for about 50 to 100 stars, known stars that are nearby your target. You measure the radial profile for these stars, and you take an average. You then have the frame PSF, or what you expect all the stars to look like in your frame. You do the same for your asteroid, and you say, if the 2 profiles match, our asteroid has a stellar-like PSF, it's stellar-like, it has a stellar-like profile, it is an asteroid. However, if your 2 frames differ, the reason for this would be there'd be an excess of flux in the asteroid, and we attribute that excess of flux to a coma. So I'll show you what that looks like here. So this is a known asteroid. This is not a fit. This is 2 separate plots here. We have the stellar profile as this line here. This is the median stellar profile from about 100 stars. And these dots represent the radial profile from this asteroid. And you can see within the uncertainties, there's no discrepancy at all between the profiles. So we can say this has a stellar-like PSF. this is not active. We then looked at a known comet, as you can see here, and this is the stellar profile again, and this is the cometary profile. And you can see clearly very earlier on, there's an excess of flux above what we see in the stellar profile. And even looking at the images here, you can see as you move out from the center, there's coma here, and even a tail up to the top left of that image. So it's that clear separation in profiles that tells you if an object is actually active or not. So out of the 16 asteroids that we looked at on these comet orbits, we found 3 profiles that were actually consistent with what we determined as activity. So you can see there's difference between 2 profiles here, here, and here. So this was in 3 of our asteroids. If we then project this 3 out of 16 into all of the asteroids in that region, we can say that maybe within this region, a third of the asteroids may actually be comets if we don't use survey imaging and we actually use deep, dedicated imaging and long exposure times. So this shows the real limits of the survey imaging here. And again, if these asteroids are observed again, and the next time we observe them, they're still showing this separation, they'll then be reclassified as comets. So quick little summary from this small project here is that we observed 16 asteroids on these comet-like orbits using deep, dedicated imaging. We observed what was consistent with faint dust coma in 3 of these asteroids. And again, these will be reclassified as comets if this activity is confirmed. About a third of the asteroids in this region may actually be active if we use deep dedicated imaging and not just survey imaging. So the final bit I'll move on to of the talk here is going to be on current work. So I'll just summarize. Again, I've kind of went over it, but these are the current surveys that we use to look for new asteroids and comets and monitor the ones that we have. So we have, Atlas, CTF, Catalina, Pan-STARRS, and in the future we'll have LSST as well, where they all bring their own pros and cons. So for example, Atlas will give you high cadence observations down to a magnitude of about 19th, whereas Pan-STARRS has a much narrower field of view, but can go down to 22nd magnitude. So the idea is here that they all have their own trade-offs. There's obviously limits to surveys, so they don't return to the same area of sky in a single filter for sometimes a week, if not even a little bit longer than that. And if we have target of opportunity observations that we need as well, this is not possible with these surveys that are on these fixed schedules. So this is where the Black Hole Target Observation Manager, or BHTOM, comes in. Lukasz touched on this last week towards the last 10-15 minutes of his talk. So BHTOM is this global telescope network made up of over 130 telescopes worldwide. Covers northern hemisphere, southern hemisphere, and they have telescopes ranging from little 5-centimeter C-star telescopes up to the medium size now 2.5-meter telescope units. And the idea is here, anyone with a telescope that wants to contribute any kind of observations and contribute to the science can do so. So what they'll do is they'll take their observations and they'll submit their images to BHTOM. They're then automatically processed and standardized in BHTOM via the Gaia catalog. And then we can use this as an effective complement to survey-based data to fill in and get these nice light curves. So currently, BHTOM is focused on sidereal objects. However, we want to expand BHTOM into as many disciplines as possible in astronomy, be that galaxies, supernova, solar system. So in the future, we want to look at non-sidereal objects, and one of the directions we want to go is solar system. So a couple of things we need to do for the system is, number one, because they're non-sidereal objects, these move relative to the fixed background. So we need to find a way to actually link these observations and link these images instead of querying the exact same RE index on the sky every time. Number two is something Lukash is actually working on just now, and it works very well, is that targets in the sky can actually change their name. So for example, as I've mentioned earlier, if you're discovered and you have an asteroid designation, and then you later on become active, you can get a new designation and a new name, even though it's the same object. So for example, I've got Chiron here that has this asteroid designation. It was then shown to be active later on and got this new cometary designation down there. So stuff like this are not difficult, but they are things that need to be implemented. And then number three is for the citizen scientists and for the amateurs that want to contribute these observations, but maybe haven't looked at non-sidereal objects before. We need to be clear and tell them how to actually observe these non-sidereal objects. So for example, if you want to observe an asteroid in the sky, you may intuitively think the best way to do that is to focus on the asteroid and follow it. However, for calibration reasons, you can't do this. So the best way to do it would be to take many, many short exposures of the asteroid and then shift and stack later on. And things like this are not difficult, but it's just communicating to the community how we actually do this. So what platforms out there just now are similar to BHTOM? Well, we have the Comet Observation Database, or COBS, and this is a well-established platform, and it receives significant input from the community, is well known about. People want to contribute to that. However, it relies on the users to actually calculate the magnitudes themselves, and you can see this may lead to a large range of these magnitudes. Also being developed just now in California at LCO, there's FOMO. So this is the follow-up observations of moving objects. And this is also based on the TOM toolkit, similar to BHTOM. And what this is going to coordinate any follow-up observations from the larger classes of telescopes, from 2 meters up to 8 meters. Intake Rubin alerts, and it'll coordinate that follow-up observation. However, it relies on people bringing their own telescope time they have already won to that system. We then have BHTOM. BHTOM is this low barrier for entry. Anyone with a telescope can contribute their observations. Anyone can contribute to the science. It does this automatic calibration and automatic standardization of the images, and everything's going to be calibrated in the same way to the Gaia magnitudes. It already has this established community of observers that want to observe and are keen to contribute. And then finally, I think one of the coolest points about BHTOM is, if you contribute any of the data, if you contribute a single data point, you can get your name on the paper, which I think is a good incentive for people to give good quality data because their name's going on the paper. But then also, if you're being published, you want to then contribute to future observations as well. So it helps out both sides. And I think the main thing to note here on this slide is not that any of these are better than the other, but they can all be very complementary to each other, and they all probe different populations and fix different issues. So in future, I don't need to go over this too much. We're going to have the LSST, which will go down to 24th magnitude. We have here the solar system of the Jupiter with the orbit of 67P here. And at the start, as I mentioned, the atlas coverage is just when it's close to the sun and just when it's bright. In future, if we have BHTOM, if we have observatories doing dedicated observations plus LSST, we can look at these comets as they go throughout their entire orbits and image them throughout their entire orbits. And this has never been done before, apart from with 67P. So this is something that's very easily achievable. And it's also, I'm a little bit biased, but this is what I would like to do in future with BHTOM. So last couple of slides here, I'll wrap up with interstellar objects. So to date, we have discovered 3 interstellar objects. So these are objects that are gravitationally unbound to a star. They come from these other star systems. They're ejected from their own system, and occasionally they will wander into a new solar system, for example, ours. What this does is it gives us this opportunity to study materials from different parts of the galaxy, from different star systems. In 2017, we had the first ever interstellar object discovered. This was One Eye Oumuamua, and you see on the top here. And then 2 years later, in 2019, we had the second ever interstellar object and the first ever interstellar comet discovered. And this is 2I Warsaw down here. So making headlines for the last 4 or 5 months, we have 3I Atlas. So this is the third ever interstellar object discovered in July this year. And these are actually the Atlas discovery images here. You can see 3I in the center. And this was discovered by the Chile unit of Atlas. I have a fairly typical nuclei to show that this to any star. These are the orbits of the inner planets. This is Jupiter here, and you can see 3I Atlas is just passing through. We'll see it this one time, and then we'll never see it again as it leaves our solar system. So tying this into BHTOM, we said, well, 3I is a really interesting object, and it's visible just now. And we need to test, is BHTOM going to work for non-sidereal objects? So we put out a call to the BHTOM community and said, well, if you can contribute observations of 3I, give them to us, you can be on the paper, and we'll have a look at it. So we had some of our own LCO time from 0.4 meter, 1 meter, and 2 meter telescopes. But then we had significant contribution as well, actually from all over the world, from the BHTOM community, who were enthusiastic and actually wanted to observe this interstellar interesting object. So 3I started when it was discovered in July within the galactic plane here. And eventually we have 3,000 total images that we got from the 4th of July up to September 11th, over 70 days. We had observations from 13 different observatories, and we watched as 3I left the galactic plane and moved out of the way there. So BHTOM does PSF photometry, which clearly in a crowded star field, this is going to be fantastic. However, for comets, as most of your signal comes from your coma, comes from your tail, so it's going to be in the wings of the profile. Really what we want is aperture photometry. So we're going to, in the future, do some aperture photometry just on this section here, where it's out of the galactic plane, and we can get nice sky background readings for those measurements. Okay, so again, I've shown you how we determine if objects are active. This was at the start when we weren't sure if it was a comet or an asteroid, but you can clearly see, as I showed earlier, the two profiles separate very early, showing that there is actually coma around what we would expect from a typical stellar profile there. And that's one of the 2 meter observations that we have from LCO. Later on, towards the end, you don't need to do these PSF fits. You can see the coma, you can see the tail. So these are really just useful when you try to determine, is this actually active at the start? So these are some very preliminary results. As I mentioned, we have over 3,000 observations in total. This is mostly just the LCO, just to guide your eye and show you what the curve will look like, the light curve. We have the calibrated Gaia magnitudes from BHTOM against MJD. We have G, R, and there's definitely eye filter up here, but it's quite hard to see with the projector. But there's eye band measurements as well here. And you can see that 3I increases by almost 3 magnitudes within this 70-day period. And we also show that there's significant contribution, and these are only about half the telescopes, but there's significant contribution from a lot of telescopes looking at this object here. Overall, this light curve is not very interesting. I shouldn't really say that, but there's no like outbursts or anything. There's no breakup, fragmentation, steady periods. It's steadily increasing as that sublimation rate increases. And as I showed earlier with the JFCs, as it gets closer to the sun, that's just going to increase and increase as the sublimation goes up. And then credit also here down to Shemek and Chris for the PSF photometry in BHTOM. So the last slide here I'll wrap up with is we also have these dedicated nightly observations. So what I showed you in that last slide here, this was over 70 days. These are on single nights here. So these are every 60 seconds or every 90 seconds. So we focus just on this bottom plot here. These are from the Observatory in Chile. This is B, V, and R band imaging. And you can see over about 8 hours over one night, there's no real change in any of the colors at all. What we may expect if the comet was getting redder, you could say something about the dust on the surface. Are we looking directly at the dust? Is there ice that's then covered by the dust? If it was getting bluer, that may tell you about the distribution of ice on the nucleus. As it rotates, are we now observing the ice as it moves around? Is there ice in patches? Is it totally covered? But as it's flat here, I think it's because the nucleus is completely coma obscured. We're looking directly at the coma and we can't actually see the nucleus and tell much about the rotational properties. So overall conclusions, if you want to take anything away from the whole talk, these are the four main important points here. So we've done, first off, this high cadence study of JFCs, looked at 116 Jupiter family comets, 34,000 images, and then we looked at how they evolve throughout their orbits. We then used deep imaging techniques from the INT to more accurately determine if these apparent asteroids were actually comets, and we just had to go deeper than typical survey imaging. And then in the near future, we would like to adapt BHTOM to process requests for solar system objects as well, these non-sidereal objects. And then as a test, as a proof of concept, we've observed 3i Atlas with the BHTOM community to see this would actually work. So I'll leave it there and I'll say thank you very much.
Thank you. Any questions, comments? So I have a question actually about water. I know you were working on dust, but it's always
sure,
for those people who don't really work, who don't do any research on comets, it's always the question of water and if comets could bring water to the Earth, and how's this research going?
Yeah, so I guess so as the comets evolve inwards, so the comets have loads of different materials on their surface. They'll have water ice, CO ice, CO2, and each of them sublimate at a different temperature. So as you travel inwards here, as you travel inwards, different volatiles will essentially switch on at different distances. So when you get to 3 AU, we call this the ice line or the water line. So within 3 AU, this is where water sublimation dominates, and this is the main driver of sublimation. Beyond this, it's typically not water ice that you would find driving sublimation. As far as water on comets bring water to the Earth, maybe I'm not sure.
Okay,
it's definitely a hypothesis, but I'm not too sure about it.
But if so, then it had to be comets that are closer than the orbit of Jupiter, right? Or do I understand it well? Because only those have like a major.
That we can see.
Okay.
So that's when it gets in this region, that's when it's water ice dominated.
So
that's when it shows up. Yeah.
Sense. Martin?
Thank you for your and I have a question. There is any connection between Trojans and this Jupiter family?
Between
Trojans?
Yeah, and the JFCs. So the Trojans are thought to have formed in situ. So they should have formed in here and not evolved inwards at all. So when the planets were forming, essentially these planets all clear out their orbits, apart from these Lagrange point closings. So there's actually a lot of effort going into people searching for activity in these objects here. So they shouldn't have ice on them because they've never been far enough out to have ice. So there's a lot of effort for people that people are putting in to actually see if they can find any active Trojans. So these are Jupiter leading Trojans and Jupiter trailing Trojans, and they're all asteroidal. And they form in situ as well.
Let's see. I have the same question.
Sure. Yeah.
Concerning this 3i Atlas,
Yeah.
because it was a rumor that it would be alien spacecraft.
Yeah.
I thought we could to show it seems to be
normal.
normal,
Yeah,
yes,
yeah.
comet. So what is special that in this that it was considered
So,
as
so initially this whole thing came around in 2017 when Oumuamua was discovered. And what happened is, so when I mentioned here, this was the second ever interstellar object, the first ever interstellar comet. That means this was the first interstellar object, but not comets. This was an asteroid flight. This showed no activity, no sublimation. It was essentially bare rock. However, it showed some non-gravitational acceleration at a point. So what we think this is this gave rise to a whole new field called dark comets, essentially. So this has been studied over in Michigan State University, and then what happens is the comets are not where you think they should be. So there's something pushing them off. So it's not like thrusters or anything like that on the comet or on the spaceship. What we think it is very low level sublimation. It's just very, very slowly pushing it off where it should be, but such a low amount that it can be resolved in the images.
So no activity is seen,
no
but
activity
you
is
see
seen.
this
That's why they're
effect.
dark comets, because they're not comets,
Yeah.
but they're kind of moving off as if they are. And then you get this one, which is clearly comet, so you don't have anything about it. But then, because when 3I was discovered, it took a little bit for the coma to be apparent. Then it was this whole, is this moving in a different way?
Much more complex.
Well, I just wanted to ask a similar question, but if we have to explain to some lay people in the streets, saying, this is a UFO,
So your hairdresser.
what should we say then? What are the evidence you should give us?
Is 3I a UFO?
Yeah.
No.
That is
So no, it looks like a comet in the spectra. It acts like a comet. It has a coma. It's had a steady increase in magnitude. Like every other JFC I showed, way back at the start of the talk, this is the first part of those plots. It's exactly the same. See, basically all of here is this little section of 3I over 70 days. It acts exactly how a comet should act. Gets close to the sun, temperature increases. There's nothing about complementary behavior from this.
Anyone else? Well, if not, let's thank Fraser. Yeah. Next week, we're going to move from comets and asteroids to brown dwarfs, right? Bartosz Gauza from Zielona Góra gonna come and give a talk. So see you there. Thank you. Very cool. Thank you. So it was perfect. I mean, very nice results, and then went pretty fine. So what are the expectations? So why we haven't seen this interstellar objects before? Is it like we didn't have like a